Dear students, today I am going to discuss about the resistances in series and resistances in parallel and temperature dependence of resistivity in current electricity. So, in step by step, we will discuss here resistances in series. If a number of resistances are connected end to end so that the same current flow through each resistances but potential difference of each resistances are changed, called resistances in series. Here R1, R2 and R3, three resistances connected in series which shown in the figures. Here three resistances R1, R2 and R3 are connected in series shown in the figure. I current flows across each resistances due to series combination because current's value is same throughout the path in resistances in series. But potential difference value changes. So potential difference across R1 is V1, potential difference across R2 is V2 and potential difference across R3 is V3. So potential difference V applied across the combination V equal to V1 plus V2 plus V3. This is equation number 1. RS, the equivalent resistances in series. Here RS, S silent for what? In series. The resistances in series, total resistances in series. From Ohm's law, we know that V equal to IRS. Similarly, V1 equal to IR1, V2 equal to IR2 and V3 equal to IR3. So here equation 1 and 2. Then from equation 1 and 2, we find that IRS equal to IR1 plus IR2 plus IR3. So RS equal to R1 plus R2 plus R3. So when a number of resistances are connected in series, then equivalent resistance is equal to the sum of the individual resistances. Now your next topic is resistances in parallel. If a number of resistances are connected in between two common points, then potential difference is same for which resistances, for each resistances, but current value changes in each resistances is called resistances in parallel. Here are three resistances R1, R2 and R3 connected in between the 2 points A and B. Then they are said to be what? Resistances in parallel. So three resistances R1, R2 and R3 are connected in parallel shown in the figure. Due to parallel combination, current across each resistances changed, but potential difference is same for all resistances. That's why current across R1 is I1, current across R2 is I2, current across R3 is I3. So total current in the circuit I equal to I1 plus I2 plus I3. RP, the equivalent resistance, means total resistances in parallel. Now from Ohm's law, I equal to V by RP. So similarly, I1 equal to V by R1, I2 equal to V by R2 and I3 equal to V by R3. Equation 2. Now from equation 1 and 2, we find here that V by RP equal to V by R1 plus V by R2 plus V by R3. So 1 by RP equal to 1 by R1 plus 1 by R2 plus 1 by R3. Hence, number of resistances connected in parallel, then reciprocal of equivalent resistance is equal to the sum of reciprocal of individual resistances. Now, our next topic is temperature dependence of resistivity. The resistivity of any material depends on the number of density of n of free electrons and the relaxation time tau. So here rho equal to m by n square tau. In case of metals, the resistivity of a metal rho inversely proportional to relaxation times. Okay, the resistivity of a metal increases and the conductivity decreases with increase in temperature. So rho equal to rho 0 1 plus alpha t minus t0. Okay, and resistivity directly proportional to resistance. So here in case of resistances, R equal to R0 1 plus alpha t minus t0. So alpha equal to rho minus rho 0 by rho 0 t minus t0, or alpha equal to R minus R0 by R0 t minus t0. Here in case of resistivity, alpha is the temperature coefficient of resistivity, and in case of resistances, alpha is the what? Temperature coefficient of resistance. ठीक है. Hence temperature coefficient of resistivity defined as the increase in resistivity per unit resistivity per degree rise in temperature, and temperature coefficient of resistance defined as the increase the resistance per unit resistance per degree rise in temperatures. Now in case of semiconductors and insulators, at room temperature, semiconductor or insulator depends on the size of the energy gap represented by Eg. If energy gap Eg is smaller and equal to the 1 electron volt, then the resistivity of room temperature is not very high, and the substances is a semiconductors. But if energy gap is greater than 1 electron volt, then the resistivity of room temperature is very high and the substance is an insulator. When we draw a graph in between resistivity and temperature, then we find that the resistivity of semiconductor decreases rapidly with increase in temperature. Thank you. Have a nice day.